Okay, students, the topic of discussion is power series solution of the differential equation of the law of radioactive decay. Okay, power series solution. Okay, so in this equation, the dependent variable is n, and independent variable is t. Okay, so in case of power series solution of this differential equation, first of all, you know that what is meant by a solution of a differential equation. Let's say the solution of this equation. What is meant by a solution of any differential equation? Okay, the question is, solution of what is meant by solution of a differential equation. For example, this differential equation, right? This is so. You must know that what is meant by a solution of a differential equation. Okay. So here the solution means getting the information about dependent variable in terms of the information of independent variable or variables. Okay, so getting, can say getting dependent variable information in terms of in terms of information of independent variable. Information of okay, for example, the solution of this one means dn over dt is equal to this minus lambda, and when solved gives the solution, gives you can say the variable capital N in terms of t. That is, for example, we have already obtained this solution n of t, that is n naught e to the power minus lambda t. Okay, so here this n is a dependent variable, right? Okay, and t is a independent variable. Okay, so this capital N of t, and as a function of time t, is solution of the differential equation. So that means the solution of any differential equation is actually getting a dependent variable in terms of the independent variables which appear in the differential equation. That means the solution of the differential equation. Okay, so now we come to the concept of the power series solution of any differential equation. Power series. Okay, before going towards the concept of power series solution of a differential equation, you must know the power series, and before that, you must know what is meant by a series. Okay, what is meant by a series? You must think about. That is, let's say the series is actually you can say the sum of terms, sum of any number of terms, any number of terms, right? That is called a series. And what do you mean by a power series? That means the sum of the terms which are in terms of certain powers of certain, you can say, expressions. That is called power series. Like means if you define the power series, okay, that means sum of terms involving powers of expressions, of powers of certain expressions, right? That series, that sum of terms in which every term is a certain power of certain expression. That sum of the terms is called as power series. Okay. For example, we come to the examples. Okay. Let's come to the examples now. Examples of power series. Examples for power series. Any example of, let's say, power series. For example, we know that this exponential function e to the power x can be expressed as 1 plus x plus x squared 2 factorial plus x cubed by 3 factorial plus so on. So this is an infinite power series. Infinite power series. Okay, because here the terms are actually the powers of x and divided by some factorial values. So this series is involving the powers of x. Okay, so that's why this is called a power series. And there are also other examples you can think about. Okay, now we come towards the idea of power series solution of an differential equation. Okay, power series solution. Power series solution of any differential equation. As the name is indicating that power series solution means a solution which is in terms of a power series, that is called a power series solution, right? So we can write a solution in which dependent variable is expressed or is you can say found or determined in form of a power series, in form of a power series is called power series solution. is called power series solution, right? For example, means if you want to solve this differential equation and you want to get power series solution of this differential equation, that means let's say you want to get the dependent variable capital N as a function of time t equal to some, you can say, power series of the terms involving 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 t, right? Because t is independent variable. So here the power series solution is actually the information about dependent variable in terms of a power series, and a power series in which almost every term involves, you can say, the powers of independent variable. That is called as power series solution. Okay, now from here we further move on word. Now the question is, how do we, you can say, decide, you can say, means the structure of a power series. Means in order to have a power series solution of certain differential equation. And because in the case of differential equation, there will be, you can say, a certain set of values of independent variable which will be allowed. So from that set of, you can say, values of independent variable, we have to choose certain, you can say, a point about which we want to get a power series solution, right? So here in this case, if we take a point, a value of time about which we want to get the information about the solution, that will be, let's say, time t is equal to t naught, right? So let t is equal to t naught is the value about which we want to get a power series solution. Okay, then the power series about this point means about this value t is equal to t naught can be expressed as, because t is equal to t naught means that time, in case of time, we know that time can normally can never be taken to be less than 0. So that's why in that case the power series can be written as, look at, so in this case you can say n of t will be written as, you can say, here an index variable small n can go from n is equal to 0 to infinity. And in this case we can, you can say, take here n, and over here so we can take t minus t naught to the power n. And if we expand this summation, we will be getting actually a naught t minus t0 to the power 0 plus a1 t minus, you can say, t naught to the power 1 plus a2 t minus t naught to the power 2 plus up to so on. Okay, right. So this is a power series. Means in case of power series, we have to decide a certain value of independent variable in the vicinity of which we want to find a power series solution, right? So this is a power series for the dependent variable n in terms of time t. So by using this, you can say, by using this power series, we can get information about capital N, right? We can put the value of t here and we already know the value of time t naught, right? So the t naught is certain starting time. In that case, we can put the value of t naught, and at any time t, we can get information about capital N only if we know these coefficients a naught, a1, a2, up to so on. So the question here is about, you can say, finding the values of a naught, a1 up to a naught, a1, a2, and so on. So here a naught, a1, a2 up to so on are unknown coefficients. Unknown coefficients. Okay, and these coefficients can be found by applying certain, you can say, conditions upon the power series. Those conditions actually, you can say, those conditions are, first of all, means we assume that this capital N of t, this is a power series solution of this differential equation. So that means this solution, capital N of t, equal to this series, must satisfy this differential equation. So that's why we put this differential equation over here, and then apply certain other, let's say, initial or boundary conditions, and then uh, we can try to get the values of the unknown coefficients a naught, a1, a2, and so on. Okay, so this way we can find the unknown coefficients a naught, a1, a2, and so on. Once the values of the unknown coefficients are found, uh, we can put those values here, and we can get, now you can say, the power solution, a power series solution, right? And that power series solution, you can say, we can see here that there are infinite number of, you can say, terms, because here the index variable n is going from 0 to infinite. So that's why in this power series solution, in this power series, we are having here infinite number of terms, and thereby means therefore we have here infinite number of unknown coefficients, right? Starting from a naught, a1, a2, and so on. And keep in mind, if there is a certain independent variable which can also have, you can say, negative values, in that case we can start the index variable, means we can also start, you can say, uh, we can start, means this is not the conditions, a necessary condition. We can start as the index variable n from minus infinity to plus infinity, even if the independent variable t is or any other independent variable is, you can say, authorized to be positive or negative. In both situations, we can start here the index variable from minus infinity to plus infinity. Okay, so here, for the sake of simplicity, I have shown here the index variable small n to be going from 0 to infinity. So even if we start small n from 0 to infinity, we go from 0 to infinity. In that case, we are getting here power series which is involving infinite number of terms. Okay, so that's why there are infinite number of coefficients to be unknown. Okay, so this is, in principle, this will be actually an infinite power series, right? Okay, now from here we move on. So the unknown coefficients can be found by putting this, so you can say, power series into the differential equation, and using, let's say, the given initial conditions or boundary conditions, so we can find out the values of the unknown coefficients a naught, a1, up to so on. Okay, so a power series, you can say, there are also special, you can say, there are examples of the power series. For example, Tayler series. And a special case of Tayler series is Maclauren series. We come towards the Tayler series. So in order to go towards the power series solution of t n over dt is equal to minus lambda, and now we will be, you can say, we will be opting for a particular, you can say, power series, that is Tayler series. And thereby we can use, and therefore further we can use a special case of Tayler series, that's in the Maclauren series. Let's do that. Okay, so particular example of power series is example of power series. Power series is let's say Taylor series, right? So according to Taylor series, we can write down the solution of this differential equation dn over dt is equal to minus lambda as. This means according to Taylor series, this capital N of t can be written as, let's say here the t is equal to t naught. Generally speaking, we are taking the starting time to be t is equal to t naught, or the value of time is t naught, about which or in the vicinity of which we want to find the power series solution of this differential equation. So over here, n of t can be written as you can say n of t naught means the point, the value of t about which in the vicinity of which we want to find the solution of this differential equation. That value of time will be used here in Taylor series. If t is taken to be 0, in that case over here in place of t naught we will be using the value of t to be 0. Okay, but this is a general value, means t is equal to t naught, means t naught might be 0, might be other than 0. So we are taking here a general case. So Taylor series actually takes, you can say, a general value of independent variable about which a power series solution is determined, is found. This is n of t naught plus and dash, instead of writing here and dash, we are writing here dn by dt. dn by dt at t is equal to t naught, right? And over here, t minus t naught will be written, and it will be bearing the power 1. Okay, and keep in mind over here we can also take this factor t minus t naught to the power 0 over 0 factorial, and over here we can write here 1 factorial plus, now plus then the second order derivative d to n over dt2, and its value at t is equal to t naught times t minus t naught to the power 2, and plus up to so on over here the factorial 2, and so on. So this is you can say Taylor series expansion, or the Taylor series solution of this differential equation. So you can label it this. Let's say this is equation 1, and equation 1 here. Equation 1 is Taylor series solution. Taylor power series solution. Taylor power series solution of dn by dt, right, is equal to minus lambda n. Okay, here interesting thing is that the Taylor series gives us the values of the unknown coefficients we were talking about in case of general power series. So here you can say generally, unknown coefficients are a naught is you can say that is n over t naught over 0 factorial, and a1 is actually you can say dn by dt at t is equal to t naught over 1 factorial, right? And a 2 is actually d2n over dt2 at t is equal to t naught over 2 factorial, and generally speaking an that would be equal to you can say dn, the nth order derivative of the number of radioactive nuclei as variable at t is equal to t naught over n factorial, right? And so on, because there are infinite number of unknown coefficient in case of infinite power series. So in case of Taylor series, these factors n over t naught over 0 factorial, dn over dt over 1 factorial, d2n over dt2 over t2 factorial at t is equal to t naught are actually the values of unknown coefficients which appear in a general power series solution. Okay, now from here we move further on. So this equation 1 actually is a power series solution, which is you can say according to the Taylor concept of the power series of this differential equation, and this is an infinite power series. Okay, so now here we will make an approximation to the Taylor series solution of this differential equation. We know that the Taylor series solution of this differential equation is coming to an infinite power series. Okay, so infinite power series means there are infinite number of terms in the series. Okay, so if we want to have, let's say, a finite number of, you can say, terms in the series, in that case we have to perform an approximation, and that approximation is called a truncation. So in this case we will let that means there are certain terms, you can say, which can be negligible. So in that case we can ignore certain number of terms, and in that case the infinite series will become finite series. For doing that, we will write down the Taylor series as, look at. So let you can say t is taken to be delta t, means one time interval, right? So means after one time, when the time has passed to equal to one time interval, in that case you can say n of delta t can be written to be equal to n of t naught plus n dash at t naught, and over here means instead of taking here means t minus t naught, because over here, because t is equal to delta t, and in this case we can take here t to be equal to delta t. Okay, delta t minus, you can say, t naught to the power, you can say, 1 over 1 factorial plus n double dash at t naught times delta t minus t naught to the power 2 over 2 factorial plus up to so on, right? So here in place of t, we are just putting means you can say t to be equal to delta t over here. So let t naught to be 0. Let t naught is 0. That means you can say n of delta t will be equal to n of 0 plus n dash of 0 and delta t to the power 1 plus n double dash of 0 over 2 factorial and delta t to the power 2 plus up to so on, right? So here the Taylor series solution becomes like this: n of delta t is equal to n of 0 plus n dash of 0 delta t to the power 1 plus n double dash at t is equal to 0 over 2 factorial delta t square plus so on. Keep in mind here n of 0 is the value of number of nuclei at time t is equal to 0, and this n dash of 0 is actually the value of dn over dt at t is equal to 0, and double dash of 0 is actually the value of the second order derivative of capital N at t is equal to t not equal to 0. Okay, so we will make here now an approximation in order to ignore, you can say, certain number of terms of this infinite series. So we will let delta t is so small that that delta t, you can say square delta t cube and so on are negligible, right? So we are letting here, if delta t is very small, in that case it's so small that delta t square, delta d cube, delta t to the power 4 and so on negligible can be assumed to be negligible. So this is an approximation we are going to make. So due to this approximation, those terms which are having delta t to the power 2 are its higher powers, they can be assumed to be negligible. And this approximation is called as truncation. Okay, so in truncation approximation, we ignore a certain number of terms of an infinite series in order to convert it into a finite series. So this means here n of delta t will be now approximately equal to n of 0 plus n dash at 0 times delta t, and all the other terms are assumed to be 0 on the behalf of this approximation, on the behalf of this truncation, right? So that's why here in this series now we are having here only two terms on the right side, and that means there are a finite number of terms on the right side. So that means now this series has become, you can say, uh, finite series. Okay, so from here further we can rectify this equation, as we can manipulate, we can process this further. N of delta t is equal to n of 0 plus n dash of 0 delta t. Okay, so that means this equation, right, is telling us that the value of number of radioactive nuclei after time delta t after one time interval can be found by putting the value of number of nuclei at the start plus the value of the derivative of capital N at t is equal to 0 multiplied by delta t. Okay, so here let's say this is equation 1, right? We can further use this equation 1 in order to approach our, you can say, power series solution, approximate power series solution of this equation, differential equation dn over dt is equal to minus lambda. Okay. Okay. So I will write down equation 1 again. So that is equation 1 is that is n of delta t equals approximately equals n of 0 plus n dash at 0 time delta t. Okay, where n dash of 0 is actually the value of dn over dt is equal to, you can say dn over dt at t is equal to 0, right? Okay, this is the n dash of 0. So we can put this we can write this equation as, in order to move further, n of delta t is approximately equal to n of 0 plus this is dn over dt at t is equal to 0 into delta t. Okay, so let's say this is equation number 2. Now, as we know that dn over dt is equal to minus lambda n. This is already known to us from the differential equation itself. So that means at t is equal to 0, we get dn over dt at t is equal to 0 means we will be getting the information of the left side and the right side of this differential equation at t is equal to 0. So dn over dt at t is equal to 0 will be equal to minus lambda and the value of n at t is equal to 0. This n at t is equal to 0. This means this is dn over dt at t is equal to 0. This will be equal to minus lambda n naught. We know that at t is equal to 0, the value of capital N is called as n naught, if we take it to be n naught. In that case, in place of capital N, we can use n naught, right? So we can put this value in equation 2 here, right? So putting, let's say this is equation 3, right? So putting the value from equation 3 in equation 1, putting the value of dn over dt at t is equal to 0 to be equal to minus lambda n naught in equation 2, we get okay, we get what? That is n of delta t is approximately equal to n naught. Now we can take this one to be n naught, means here n of 0 is same as now n naught, right? So n naught plus you can say here we can put its value minus lambda n naught times delta t. Okay, so we can further rectify this equation to be n naught minus lambda n naught delta t. So this n of delta t is approximately equal to this one, right? Let's say this is equation number 4. Okay, means after one time interval, after t is equal to delta t, the value of you can say number of radioactive nuclei left to further decay, that will be equal to the originally present number of nuclei minus the decay constant lambda multiplied with the originally present number of nuclei multiplied with the time interval you are taking. And this delta t is taken to be very small. That means this is less than 1. Here, keep in mind here that this delta t not right, this delta t is you can say very small as compared to 1. Otherwise, we will not be able to assume that it's secure and it's higher power, means delta to the power 2, delta t to the power 3, and so on. They are negligible. We cannot assume them to be negligible if delta t is not, you can say, smaller than 1. So here you have to keep in mind this delta t, the time interval, is needed to be, you can say, very small, so small that this is 1, are very small as compared to 1. So Equation 4 here gives us a Taylor series approximate solution after one time interval delta t. Okay, and if we take a large number of time intervals, we can further, you can say, we can further use this equation 4 in order to move forward. Okay, so let's do that. So here, if let's say there are two time intervals passed, means if t is equal to 2 delta t or t is equal to 3 delta t up to so on, then how do we get n of t, right? This is a question, and we know that after one time interval the value of n is what? N naught minus lambda n naught into delta t. Okay, and as you know that here keep in mind that n naught is equal to n of 0, and this can be written as n after 0 time intervals. After 0 time intervals, so it means the originally present number of nuclei are actually at the starting value. That means the value of number of nuclei after 0 time intervals have passed. So if we know the number of nuclei at the start, means at after 0 number of intervals have passed, in that case we can find out the number of nuclei which are after one time interval. Means on the right side this information is here, and naught is actually n after zero number of time intervals, right? And here n of delta t is n after one number of time intervals, right? Okay, and n of 2 delta t will be then n after, you can say, 2 number of time intervals have passed, and so on, right? So from here, from this equation, we can see that if we want to get the value of number of nuclei after one time interval, in that case we need the information about n after 0 number of intervals. And generalizing this equation, we can write down the general expression for this equation. Okay, so generalizing this equation, and this equation, let's say, can be named as, let's say, equation A. Generalizing equation A, we can write down that n after, you can say, I number of or I plus 1 time intervals, this will be equal to n of I minus lambda n I delta t, right? Means it is general, you can say general form of the equation A, because in equation A we are looking at that if we know the value of n after 0 time interval 0, then we can find out the value of number of nuclei after one time interval. And similarly, if we want to find here the number of radioactive nuclei after I plus 1 time intervals. In that case, on the right side, we must know the value of a number of, let's say, radioactive nuclei after I number of time intervals. In the here you can say here I can be taken to be starting from 0, 1, 2, 3, and so on, right? And if we put I to be equal to 0, over here there will be n naught minus lambda n naught time delta t, and over here we will be getting n of 1 delta t, and that will be the equation A. And similarly, if we know, let's say, if we know n1, that means I is equal to 1, and so in that case on the right side it will be appearing n1 minus lambda n1 delta t. So in that case we can get the information about the radioactive nuclei after 2 time intervals have passed, that is n2, and so on. So here, for the sake of simplicity, we can further, you can say, drop here the symbol of delta t, and we can write down the equation which is called as iterative equation like this. Look at over here, dropping delta t, dropping delta t, right? That means n I plus 1, and writing the index I and I plus 1 as subscripts, we can write down ni plus 1 ni minus lambda ni times delta t. And we will be dropping here only the delta t from the, you can say, the dependence here. Not overall dropping, means we are dropping here delta t from, you can say, from left side, right? Unless in that case, this will be, you can say, the equation which is famously called as iterative equation. And let's say this is equation B, and equation B actually approximately gives us a power series solution in form of iterative equation. This is a power series solution in form of iterative equation. For this equation, dn over dt is equal to minus lambda, and after we make the truncation approximation for delta t to be very, very small as compared to, let's say, 1. Okay, thank you, students.